is about as far as you can get from the airport. So the last time I was in Pittsburgh was 2016. And before that was maybe 2010. So we are independent. All right, well, it's 7 o'clock. Let's see if a few more people drop in. Since we only have 4 papers, we can wait a couple of minutes for everybody to put in their appearance. Okay, Jai is here.
Hey. Hello.
Stay. All right. We will get to it. Maybe you're going to have a small audience tonight. But if you're going to Pittsburgh, you'll get to do the talk live there, right? So this is your rehearsal.
1 of 3.
Yeah, so getting to Pittsburgh, I checked some airfares and the like, and it's like $800. $800 you can fly to Singapore.
Yeah, that's awful. Which carrier was that?
All of them.
All of them. Okay.
even Southwest.
Wow.
And if you go with Delta, you have to change planes in Salt Lake City. And if you go with American, you have to change planes in Texas. And that makes it an international flight. It's just not at all easy to get there. So
I wasn't given that option at all because I'm from Australia. And,
yeah.
Since the conference was hybrid, they're like, no, you're not going. It's too risky. COVID.
Yeah. No, that's the right call. I mean, where the conference is going to come to you next year.
Yeah.
So it's been a long time since I've been in Melbourne, but that's already on my calendar.
Yep.
Hope to do
It'd be
that.
nice to
All
see
right.
you here then.
So I think we may as well get started since we have a few more people who've dropped in on us. So welcome to Tools and Environments 3. And we have 4 papers for you in this session. The first of these is the author is senior author is Chris Timperley, and he's a special faculty member in the Institute of Software Research at Carnegie Mellon. And the title of his talk is Understanding and Improving Artifact Sharing in Software Engineering Research. Chris, all yours.
All right, thank you very much. Yeah, let me set up the screen. Okay, can we see this all right?
Yep.
Everything good?
Yep. All good.
All right, cool.
Yes.
Thank you very much for the introduction. Okay, so today I'll be introducing our paper, Understanding and Improving Artifact Sharing in Software Engineering Research, which was originally published in Empirical Software Engineering last year. So before I begin, you probably want to know, what do I mean by an artifact? Artifacts are the tools, benchmarks, and other resources like data sets that are created during the course of a research study. Looking back over the last few years, in our study, we found that most papers in software engineering provide some form of link to their artifact as part of the paper. This sharing of artifacts has significant benefits for the community. It provides evidence for important results. It helps to improve the understanding of a research paper by providing an implementation or additional data. and it allows others to extend and reuse tools and data sets in subsequent studies. However, a key problem with this informal artifact sharing via links and papers is that you get no guarantees about artifact quality. When you click that URL in the paper, you don't know what you're going to get. The link might be dead, the artifact might have never been uploaded, you might be unable to build the artifact, there might be no documentation, or it might do something completely different to what's described in the paper. So how can we avoid some of these quality issues and tap into the full potential of artifact sharing? So one solution to the problem is artifact evaluation. And during artifact evaluation, authors are invited, after they've had their paper accepted, to submit their artifacts for evaluation. If it's successful, if it passes the review, they get awarded a badge that appears in their paper. However, despite the spread of artifact evaluation, you see this year at ICSE, it's at FSE, ASE, so on, we found that very few authors actually choose to participate in artifact evaluation. So one way of saying this is that while most papers informally include artifacts via URLs, very few of them are formally evaluated. So how can we bridge this gap, get more authors to participate in artifact evaluation, and ultimately improve the quality of artifacts? To bridge the gap, we teamed up with Lauren Herkis, an expert in the field of implementation science. Implementation science is a relatively new discipline that tries to explain the gaps seeks to identify the gaps between the theory and implementation of certain ideas. So implementation science originally comes from healthcare, where it's used to try to understand why certain treatments that work well in the laboratory or in clinical trials can take decades to actually make it into routine practice. In this study, we view artifact sharing and evaluation as an implementation problem and try to understand the barriers that affect artifact creators, users, and reviewers. To identify those barriers, we conducted a mixed method study with 3 components. We examined 5 years of publications at various software engineering venues to determine the prevalence of informal artifact sharing. We looked at participation rates at artifact evaluation tracks at those venues. And finally, we conducted an open-ended questionnaire of paper authors. Following an analysis of our results, we identified 12 challenges that affect creators, users, and reviewers of artifacts. To learn more about those challenges, you're going to have to see the paper and the longer version of the talk, I'm afraid. From those challenges, we derived 8 high-level recommendations aimed at different stakeholders, ranging from individual authors to professional organizations such as IEEE and ACM. So in the time that's left, I'm going to talk to you about a few of those recommendations. One of the challenges that we identified is that it can be costly, time-intensive, or impractical for reviewers to perform evaluation of certain types of artifacts. For example, fuzzing and program repair experiments can take weeks or even months to run. One way to combat this problem is to provide artifact reviewers with cloud computing resources. Optionally, we could even give authors access to a cloud instance prior to a review to allow them to try to preempt and address any issues that might occur. Of course, all of this requires money. To help to cover some of these costs, funding agencies and professional organizations might consider creating supplements for artifact-related activities. Finally, another challenge that we observed was that authors find artifact badges and their associated evaluation criteria to be vague and confusing. To solve this, we propose that authors make explicit claims about their artifacts in a document that's provided with the artifact that can then be evaluated by reviewers who can leave their feedback in that same document, which can then be seen by prospective users of the artifact, which helps to set expectations between users and creators. To see more of our recommendations and results, please read the paper and watch the longer version of this talk. Thank you for listening, and I look forward to answering your questions.
Great. Thank you very much. That was good. We'll come back and take questions at the end. If people have questions, they can either hold them and ask at the time, or you can post them in the chat window. Okay, so let us move on. Our next speaker is Jai Cannon from Deakin University. He's a PhD student in the Artificial Intelligence Institute there, and his research is around improving the fragility of machine learning systems. and has practical experience as a software engineering before that. So, Jai, over to you.
Am I audible to everyone?
You are. Yep, cut.
All right, perfect. So just to give you a brief context, this presentation was an initial concept for my PhD, and I've just finished my COC in the past few days. So this was one of the key points that we presented. All right. So hello, everyone. My name is Jay Kannan, and I'll be presenting my paper, ML Smellhound, a context-aware code analysis tool. The benefits of code analysis are well known, and machine learning codes stand to benefit from code analysis tools. In my research, I'm studying the applicability of code analysis tools to machine learning code. However, code analysis, when applied to machine learning code, suffer from false positives. The definition of false positives are prone to subjectivity, which is often influenced by the programming language and the developer's perception. To balance the problem of false positives, tools need to be calibrated using some sort of configurations. However, choosing the correct configuration to analyze code is also challenging, as incorrect configuration can lead to permissibility of defects. In our research, we hypothesized that the inclusion of context can improve the identification of defects via the reduction of false positives. We provide an initial concept of context as features from the problem domain, purpose of the code, lifecycle, environment the code is developed in that influence the output of code analysis tools. To further understand the context, we believe that the characteristics of code are an important factor to consider during the analysis of source code. For example, the code on the right is taken from an open source machine learning project. In the code, we see that the use of single letter variable names and the mathematical nature in the red boxes. According to PEP 8, or according to Python conventions, the use of single letter variable names is not permitted or not preferred. However, in mathematics, the capital single letter variable names are used to represent matrices. Furthermore, as you can see that the code is implemented very close to the mathematical counterpart or the mathematical equation. In our research, we want to investigate if considering these characteristics of code as context can improve the results that are provided by code analysis tool on analyzing such code. We also want to investigate if including these characteristics as context can better allow us to better understand and identify machine learning code smells. To test our hypothesis, we implemented a prototype of a tool using Pylint. Pylint is a Python linter, and our approach uses a context meta model, which identifies the type of code and determines what context to apply. A set of context transformations that apply and set configurations and rules for the linter, and context checkers that check for machine learning code smells and generate a contextualized audit report for the end user. In our prototype, we use the concept of the problem domain to implement the context meta model. We use the problem domain to check for the file level imports. Now, based on the imports, we analyze if the file being sent into the code analysis tools is a machine learning versus a non-machine learning code file. We then apply a set of transformations using the context transformations to set Pylint rules. The transformations include addition, where we've added certain custom rules, subtraction, where we disable certain rules on the code, remessage, where we've reworded some rules for better understandability, and reprioritize, which re-ranks certain rules. We use a context checker that uses these configurations to check for machine learning smells and generate a contextualized report for the end user. For our initial evaluation, we analyze a block of machine learning code using Pylint with the default configurations. In the analysis, we see that the variable name df is picked up as a violation. However, in machine learning programming, a df is used as a common acronym to indicate a data frame. Next, we apply context to Pylint and analyze the same code And we see that this violation is no longer present. To further our research, we plan our research in 3 phases. In phase 1, we conduct a systematic mapping study where we plan on mapping existing code spells to known machine learning faults. We then conduct a quality where we interview practitioners to identify the relevant context and code spells that are varied during machine learning development. We use the findings from phase 1 to refine the definition of context that we've created, and then to create the context meta model. We apply context models to annotate a set of machine learning code and machine learning code smells. And we do this process iteratively and evaluate if context is useful in improving the precision in detecting machine learning smells, as well as reducing false positives. We then use these findings to develop the full version of the tool. In phase 3, we evaluate if context is effective in reducing false positives and in detecting machine learning spells in a controlled study with practitioners. And that's it for me. Thank you very much for listening.
Perfect. Thank you, Jai. That's good. All right. So here come your messages. All right. So the third paper is being presented by Felipe Kogo, and who works for Huawei in Canada. He's a principal researcher there, working to develop automated solutions that help productivity and trustworthiness. He's a PhD from Queen's University in Canada. So the title of his talk is Towards Build Verifiability for Java-Based Systems, and the name on his identification there is not his, but Felipe, go ahead.
Thanks for the introduction. Well, I hope everyone is seeing my presentation. In case not, please let me know. So my paper is titled
it's not visible.
Towards Build Verifiability for Java-Based Systems. It's not visible?
Yeah, we can't see our presentation.
You have to share your
screen.
I think we lost him.
Yeah, I think he dropped out.
Mm-hmm.
The platform is a bit finicky. For some reason, my unmute button wasn't working.
That's a very polite way to put it. I mean, you know, it's a project.
Sorry about that.
Back to you. All right, try to share your screen.
Some technical problem here. All right.
Yeah.
Okay, let me try again. How's it now?
No, we still don't see it yet.
No.
You're frozen for me for some reason.
Zane, can you help?
I froze. Oh, that's so sad.
Yeah, so if you click on the start sharing my screen at the bottom left.
Mm-hmm.
Yeah, so after you click on...
It's the fourth icon.
Yeah, I did so actually. Yeah, no, like there is a message on my browser saying failed to publish screen. Oh, did you click cancel? Right. No, I didn't. To share, choose a screen. Okay, yeah, let me try it one more time. Sorry about that.
All right. Well, we're not pressed for time.
Are you on a Mac?
Okay.
I am.
Ah, me too.
No, I'm on a Windows.
Felipe, the other alternative is
and use Chrome. So, yeah.
Yeah, the other alternative is you can maybe email me your slides and I can share from my screen if it doesn't work, if sharing your screen doesn't work.
Okay.
So, maybe what we should do is go ahead with Trey's talk, and then we'll come back to you and see if you get it all sorted out. Okay.
Sounds great.
All right. So the fourth speaker in our session is Trey Woodliff, and he managed to get his up there. So as you can see, the title of his talk is Semantic Image Fuzzing of AI Perception Systems. Trey is a PhD student at UVA who's working on developing methods at the intersection of software engineering and robotics to ensure the safety of autonomous systems in the real world. All right. And so over to you, Trey.
Great. Well, thank you for the introduction. As said, I'm going to be talking about our paper, Semantic Image Fuzzing of AI Perception Systems. My name is Trey Woodliff, and I'm presenting on behalf of Sebastian Elbaum and Kevin Sullivan of the Lab for Engineering Safe Software at the University of Virginia. So let me lay out the vision for this work. Existing autonomous system test suites achieve poor semantic coverage, and the methods to increase this are limited. And thus, we want to introduce the idea of local semantic test case mutation to generate realistic and novel test cases to expand semantic coverage. And our experimental results show the ability to uncover perception failures in state-of-the-art systems. Our technique generates novel perception test cases at a low cost that extend real-world semantics in a realistic way. As an example, here we see how our technique can perform a local semantic mutation to an existing real-world test case. On the left, we see a mostly empty roadway with the sensor input above and the expected interpretation below. This provides a useful but not very challenging test case. On the right, our technique has performed a local semantic change by adding a car to the roadway, and it does so in both the test input and expected output. In this way, we generate a realistic test case that covers a new, semantically different scene. Existing testing techniques make trade-offs between the realism and ability to achieve semantic coverage. These techniques achieve success in only one area, limiting the ability to achieve meaningful semantic coverage in a realistic way. This is where we come in. We want to combine the best of these techniques to perform local semantic mutations on real data while ensuring that the resulting test case is also realistic, allowing us to achieve high semantic coverage and high realism. For example, here we use local scene semantics to isolate this red car in order to mutate it into a blue car. Let us see an example of the technique leveraging prior test data using the open roadway from before and mutating it to add a car. First, the system must find a suitable car. To do so, the technique leverages the available data and searches for a viable candidate. In this case, it selects this image. The technique then isolates the car, being mindful of its local semantics, and checks to see if adding the car to the roadway will result in a realistic test case. We call this step the conformity check. The goal of conformity checking is to ensure that we retain the realism of our data with respect to the physical world. We accomplish this by designing validation rules that guarantee realism is respected. The considerations vary based on the mutation, but the main idea is that we can use domain-specific knowledge to craft validation rules. Ensuring that the new test case is realistic is a crucial part of the pipeline, as not doing so can lead to false positives. For example, here a brightly lit car has been added to a shaded street, which is not realistic due to the inconsistent lighting. Thus, we introduce a conformity check for lighting. Moving back to the example before, if the conformity check is successful, the technique then combines the two to form a new test case. Formal definitions of how our technique leverages prior data to perform local semantic mutations while preserving realism are available in our paper, and a Python implementation is available on our GitHub, linked here. We explored 3 mutations to examine our technique's ability to test perception systems, including the car color change and addition that we saw before. We also explored a mutation for adding a person to a scene. This is one of the key advantages of our approach, as it extends semantic coverage with this new test case without needing to set up such a hazardous situation in the real world. Now let's examine our experimental results. To test the performance of our mutations, we generated 150,000 mutations, which we tested on 5 state-of-the-art perception systems. From these, we found 883 mutations that led to just over 1,200 inconsistencies, where more than 1% of the image was misclassified. These are both just a fraction of a percent, which is good. These are state-of-the-art perception systems, and we expect them to perform well on the overwhelming majority of test cases. This highlights the importance of our mutations to search out the rare but impactful test cases that can uncover these failures. In addition, we found 20 extreme inconsistencies where more than 10% of the image was misclassified. Let's look at one example now. Here we see the performance of the efficient PS perception system for a scene in which a white truck is entering an intersection. As shown in the upper left, the perception system originally identifies the truck. Then the mutation adds a car in the intersection just in front of the truck, shown in the upper right. Then the performance on the mutated image falls drastically, as shown in the lower right. This is potentially a safety hazard if the system cannot detect moving obstacles in the roadway. In conclusion, we introduced the notion of local semantic test case mutation that allows us to leverage existing annotated real-world data to generate realistic and novel test cases to expand semantic coverage of perception systems. Our long-term vision is a time when autonomous system testing is measured not by millions of miles driven, but by semantic coverage of real scenarios. Thank you.
All right. Flew through that one. Okay. Felipe, should we give this another try?
Yeah,
Ready to
let's
go?
give another try.
All right.
Sure. If it doesn't work, I think I can make it without the presentation.
Yeah, I've had to do
Okay,
that.
let's see. How's that now?
Nope.
Not yet. So if you are on a
Yeah.
Mac,
Okay.
you
Yeah,
have
I
to-
guess I can make it without my slides. I'll be looking at them and try to explain to you all what we did, right? Unfortunately, you won't see the visual clues, but I believe I will try to be clear here. So again, like just a quick context, our work was made by me and my colleagues at Huawei and Professor Jack Jang on the York University at Canada. And we tried to come up with a solution for producing verifiable builds for Java-based systems, right? So let me start explaining what a verifiable build is. So when you build deliverable packages, right? Occasionally, every time you build a deliverable package, you produce different binaries, right? So every build instance will, when you hash the binaries, you will see that the binaries are completely different, right? So when that's the reality, you simply can't verify.
did we
You froze.
lose Felipe?
Yeah, I think so.
Okay. Yeah. Well, I think he may be able to rejoin a second. I had some connection
Different
with
packages, right? So
Now he's back. Nope. Yes.
simply put that in a repo and say, look, this is where it also improves quality assurance. So again, like for some stakeholders in the industry, achieving verified builds is really something important. So we came up with this approach.
Yeah. This is not going the way we had hoped, is it?
I think
Yeah.
I was having internet issues.
Yeah. Well, I was having issues connecting to Midspace earlier as well. Like it was just kept on refreshing. So
Seeing like a warning icon on people saying video quality may be limited due to an unstable connection on like half of the people here.
Yeah.
So
Yeah,
yeah.
Well, for what I pay for my internet connection, it better be stable.
yeah, that's why I came into work to ensure that this doesn't happen to me at home.
Yeah. I mean, we pay a lot for our internet connection here. Of course, part of that is American capitalism, but part of it is our buying a good service. Otherwise, you can't stream all those movies.
Yeah, that is
So
true.
I think so we'll give Felipe another minute or two and see if he returns.
I think if anyone is able to get into touch with Felipe, should message him saying, "Hey, can you switch over to a hotspot or like a phone hotspot?"
Yeah, but
and then try it. Probably it's better.
it'll be 20 minutes from now, so you could do it with his telephone, but well, you can't bat 1,000. I mean, it seems to be the a rule of law somehow that you can never run a perfect demo. You can never have a perfect session. It's that's why we have software engineering. If everything works perfect, they wouldn't need us.
In all context, when this happens to us, software engineers, we complain about the same thing. We have the same line of questioning.
It's always technology.
It's always technology, never us.
Turn it off and on again.
But you need is it plugged in? It's comes with the territory, I'm afraid. So
if Z was presenting, it wouldn't be an issue for him because you can switch to the whiteboard directly behind him.
Right.
Like just do it on the whiteboard, old school.
So while we're waiting, I know we don't have too many people here, but if there are some questions on any of the previous presentations, maybe we can take a couple of questions and then see if Felipe returns.
If so, I'd like to start off with a question for Chris.
Go ahead, please.
It's not a question as such, it's more of an observation. As you mentioned, like sharing artifacts is a difficult process. And even for my paper, I had code, but unfortunately the code that we did was on our private GitHub. So we had to share it using like Figshare or some there's a code.
Oh, interesting. Yeah.
Yeah, so the artifact is there. So however, like we've been developing on it on our side and on Git, and every time we push updates to Git or modify it, we can't change that artifact there, which means basically using a zip and then publishing it or that, which becomes tedious. And once the project like expands or moves on, you kind of forget about that implementation.
Yeah, I totally agree. Are you using GitHub in particular?
Yeah.
So if you're using GitHub, then just a small suggestion, you can hook it up to Zenodo, and then every time you tag a release, it will create a new release of your artifact on Zenodo. So you can even see that somebody's updated like a new version of this. Still doesn't solve a bunch of issues, because if you have a really big artifact, like we had one for a paper where it was 40 gigabytes and Zenodo will only allow you to do 50 gigabytes. Try to upload version 2. No. That will exceed the file limits. So,
So
also,
go ahead.
Now, also, like if you are on a private Git, like an internal Git, you don't want to have like a public access to that project in that sense. So yeah, definitely, I see the use of that. So if there's like a Git for sharing artifacts, like a similar implementation, I think it's a very useful approach.
Yeah, I have a kind of similar issue to the one Jai just raised, which is some things are proprietary. Right?
Yeah, absolutely.
That I'm perfectly willing to give a talk about the results of my research and to share certain results, but I don't want to show you the code, because I live in a world of startups, and
Yeah, yeah.
people worry about that a lot. So the issue of artifacts becomes tricky there. I mean, you don't want to attach a non-disclosure agreement to an artifact.
No, no. It's really interesting you mentioned that because so we did the survey. We got I think it was like 143 responses, and we got a good chunk of them who mentioned that as a specific issue, like it being private code and so on. And they specifically mentioned that during like review or at the conference, they'd been criticized for not sharing their artifacts. So there are times when the community needs to maybe take a step back, and not everything needs to share its artifacts. Because the community is kind of moving in a direction now. Like even ICSI this year, you could upload the artifact with your submission, which is good. But you've got to be careful not to exclude industrial authors.
Yep, absolutely.
Right. Yeah, good. So it looks like Felipe has managed to rejoin us. Welcome back. Do you want to try to share your screen again? Or do you just want to continue with your talk?
Okay, I can try. Sorry,
Not ideal,
I have
but
no
may I
idea where I
suggest audio
dropped.
only?
At which point it was when I dropped. So
You
I actually
have not
completed the
gone
whole
very
presentation.
far.
So you guys.
Yeah, it was just at the beginning.
Okay.
Where
Yeah.
Yeah,
I would say
so
the last thing was hashing artifacts.
Yeah. Call the previous one a rehearsal.
All right. We have 25 minutes here, so maybe I can kind of try to wrap up my presentation, and we can generate some discussions. So again, sorry about that. I presented early today, and I had no technical issues, but again, so let me try to wrap up my presentation here in less than 5 minutes, probably. So I was explaining probably about build verifiability, right? And what is that? So we build twice, right? The same program, the same application, and we expect to generate the same binaries, the same deliverable packages, right? It turns out that that's not always true. Sometimes we have unverifiable and unreproducible builds that every build instance will generate different binaries, right? And that might be a problem to a lot of different industrial stakeholders, because eventually, you need to certify your build and certify that a certain source code that you provide to your customer, it's actually generating the binaries that you are distributing in the wild to your customers as well, right? So that's the importance of having verifiable and reproducible builds, right? So we consider that a build is verifiable when the build is reproducible, which means you always generate the same binaries, right? Or you are able to explain the difference that you see in the binaries every time you build, right? And again, it turns out that it seems like an easy thing to achieve, but it's not, because you have different source of non-determinism that can affect the reproducibility of your build, right? I will give a very simple example. Like if your build generate timestamps in the binaries, right? Every time you run the build, you're going to have different binaries. If you hash the binary, right? You're going to achieve different binaries. So we came up with an approach to help developers generate verifiable and then reproducible builds for Java applications, right? So basically our approach is based on 5 steps. The first steps basically generate 2 builds, like having 2 build instances in which you generate binaries and you compare the contents of the binaries. If they're the same, or you can explain eventual difference in these binaries, then you don't need to do anything else. You already have a verifiable build, right? When you don't see these, like when the binaries are different, or you cannot explain this difference, Then you go to the second step of our approach, which basically diagnose the source of non-determinism that might be affecting the verifiability of your build, right? Basically, we consult with specialists or we consult documentation to kind of figure out what these source of non-determinism could be, right? So once you identify them, you try to mitigate those sources of non-determinism. And in our approach, we use two tools that we developed that basically dynamically change the byte codes of the binaries and the build tools as well, right? So usually we build using Maven, Ant, or Gradle, right? And these are Java by themselves, so we leverage the Java API instrumentation to change the bytecodes of these build tools such that they always produce equivalent binaries, right? In our fourth step, we basically document the steps that we have to go through to produce the equivalent binaries. And in our last step, we simply output the equivalent binaries, right? To evaluate this approach, we set up a case study using a repositories of packages Java packages that could not have their build reproducible or neither verifiable, right? This repo is called, it's actually an open source project called Reproducible Central. So if you Google that around, or if you go on GitHub, you're gonna find this Reproducible Central project. And there are 46 projects with 112 releases that could not be verifiable verified in this Reproducible Central project. So again, like we ran our approach, and we could, from the 46 projects that we saw in there, we could generate verifiable builds for 42 of them. And we also explored 13 commercially adopted within Huawei Java projects that we could also make their build reproducible using our approach, right? In our paper, you will also find a catalog of different patterns of source of non-determinism that can be very useful to industrial practitioners to, reuse all the knowledge that we generated during the application of our approach. So I invite you to take a look in our paper. There is a very thorough explanation of these source of non-determinism, right? So in summary, this is what we're going to find in our paper. I invite you to take a look in the paper, and I appreciate your time. And sorry again about the technical issues that we had. Would be much better to see the slides, but I tried my best here to kind of explain without those visual clues here. Thank you.
Well, thank you. I think that was well done, and it forces you to kind of reorganize your thinking on the fly, and good job. All right. So
thanks. Thank you so much.
Yeah. Well, I had a similar experience some years ago. I was all prepared to give a talk. I had my slides all set up, in a classroom with a bunch of students wherever I was, and then there was I can't remember if it was a bomb scare or a fire drill or something, but they threw us out of the building. And this was in Lower Manhattan, if you know your way around New York City. And so my host said, well, why don't you just give your talk? And so here I was out on the sidewalk, right? With no slides and people, some of whom were part of the university and some of whom weren't. So you have to adapt, right? So good job on that.
Yeah.
So does anybody have any questions for Felipe?
Thank you so much. Yeah, this sort of situation becomes a story, right? So you have something to tell.
Yeah, but you become comfortable with your material, and then you can make it up as you go along. And if somebody says, oh, speak for 10 minutes, you can do 10. And if somebody says, oh, you have half an hour, so yeah, you know more about your subject than anybody else here. So any questions?
I'll go ahead and ask you a question, Felipe. So I think you mentioned kind of motivation for this being like supply chain attacks and like interdiction. Is that, do I have the right understanding there?
All right. Let me make questions then. I will try to, steer some discussions and maybe, might be totally informal, but just for curiosity, like, how many of you guys knew about this problem of build reproducibility and build verifiability? Because I came across this software engineering problem probably around 2 years ago. And to be honest, I had no idea that there was a big problem, right? And this is actually becoming more and more important because of this problem of supply chain attacks, right?
Yeah.
I think that there was a very famous attack a few months ago, I believe, on the solar winds, and I think that these build reproducibility was one of the solutions that could kind of avoid this sort of problem, because you simply can't kind of hijack the build process when you ensure that your build is reproducible, right? So I was just curious on how many of you actually came across this problem before?
Yeah, I have. I was wondering, are you familiar with the SPDX effort? The Software Package Data Exchange?
Yeah. For SBOMs, right?
For?
Oh, no. I think you're
It is.
talking about
Yeah, you're
another
right.
thing?
It's software bill of, yes, it's software bill of material. Right. I mean, it's an
Yeah.
open standard.
Yeah.
And,
yeah. Mhm.
and so it seems to me that what you're doing is fairly close.
Absolutely. Yes. Yeah, again, I think supply chain is something that ties together to all of these, right? Software bills of materials. So first step is to know what's in your soup, right? And then to ensure that the ingredients are the real stuff.
It gets interesting in open source projects where you have a product that's composed of a lot of other open source projects. What do you do? It's very common for those upstream components to be updated frequently. And so now I have an application that's out there in the world that's built on all these things, and suddenly there are any number of updates to those things. What do I do? My application appears to be working okay. Do I mess it up with these new pieces, or do I have a staging area where I run a standard set of tests against the new ones, and do I validate? Is there some kind of a certificate of ownership of the newly delivered components that tells me that they are in fact the right ones, rather than, as you say, something unverifiable?
Yeah, absolutely. Well, what I see people doing nowadays, it's using what they call these dependency bots, right? They basically do the upgrade for you of your upstream dependency, run your test suites, and check if nothing was broken, right? But I see that in the future, probably we're gonna have more features, as you said, probably a repository of components that are jointly verified, and then what you are downloading, like the new version that you are downloading, it's really something that it's not hijacked or wasn't anyhow kind of changed during the download to your own production system, right?
But this all gets into the whole.
And I'm also curious to see.
Go ahead.
Sorry.
I was just saying it gets into the.
No. I was.
Let me try. It it gets into the continuous integration DevOps area because, sometimes there are now these automated build tools that now they get this component delivered to them, and the automation says, "Oh yeah, build it," so we've automated. We've done such a good job of developing the automated tools for incorporating these upstream updates that it becomes easier and easier for somebody to spoof an existing component and hack a system that way. And it seems to me that that's an important practical application of what you're trying to do.
So, Felipe,
Yeah,
just
that's
a quick.
true. And the CI and DevOps thing also comes with very fast release, right? So you put things in production before you really can't know, what's in there. So sometimes you're going to release things that, as you said, something was spoofed into, and yeah, maybe you take days until you realize that you put something in production that you shouldn't, right?
Felipe, I believe the problem that you're addressing, if you move one layer of abstraction above that, if you had to generalize the problem, you will find that that's a very important aspect, especially in the domain of machine learning, is because you train a model.
That's what I was about to say, yes.
Yeah, you train a model using some sort of a historical data that you've got from somewhere. Now, you don't know what the model has learned. That is, you can't verify that until and unless you see what prediction it's making. And now you can't go in and you can tune the model, yes, but you can't teach it. So you have data and then you produce the results and it's what is this now? Similarly, when you take that model and put it into a stream environment, now the data is no longer historical, it's more like stream data. Then you have a completely different set of predictions. And because in machine learning, if I was to have a model or a classifier that classifies apples and oranges, and if I gave it a photo of let's say this cell phone, it's never going to say oh, it is not an apple or an orange. It'll say it's 35.33% an apple or an orange. So yeah, the verifiability or verification is a very crucial step to reproducing results, which is actually a very big problem in the domain of machine learning, is because reproducibility of results is it's close to difficult / impossible, is because you don't know what the model learns. So if I run 2 iterations of the same model using the same data, one will have 98% yes, and the other one will have 94. You don't know why it's different, although you've used the same settings, same parameters. Very interesting.
For sure. One of my co-authors in this paper, actually, you were saying Boyu Chen on my name. I'm Felipe. That's one of my co-authors. I had a registration problem, and I'm using his account. But he has a paper on ICSI about machine learning models reproducibility as well. So you might be interested in this paper too. And yeah, you have pretty much, as I was saying, you have different source of non-determinism in there, right? Even the seed that you choose might change a lot the performance of your model, right? And now, as you were saying, the machine learning models are just historical data and real-time data and so on, and verifying all this, while the system is running, while the model is deployed, and if the model might be causing some harm to someone, these are things that I believe you guys in the AI community will probably be looking into very soon, right?
Yep. Because that's where I was focusing my research on as well, is because you have this different aspects of the way you write code. It also depends on the people who are writing it, because people who write ML code generally are not software engineers. They're more from the scientific programming background, and they have an influence of that in their code. Open up any machine learning code, go through it, you will see implementations of algorithms. For example, you can copy that code to like a notepad, and then just go and find the algorithm that implements that code, the actual mathematical algorithm. You'll find extreme similarities between that. So, and how this affects like the analysis of code it's actually quite complex. It's because now something that developers want is code quality. They want a faster release cycle. They want their builds to pass before they chuck it into CI and like release it. And now you have something like this where it goes against all your programming practices and principles, and you don't know if like an output that is generated by a code analysis tool saying like, hey, XYZ is the line too long. Now, when you look into that line too long, there's like magic numbers, there's declarations, there are some values. Now, you don't know as a software engineer, like, is that a part of an algorithm, or is that like mathematical? For example, pi equals to 3.14. There's declared somewhere, like, is that a part of the algorithm, or is that like something just there? Is that a problem with the test? So you need to, so that's where we want to identify these characteristics and like put it into tools saying that, hey, listen, I know you're in the development phase, so this is permissible, but as soon as you move into production phase, context will come in and say like, hey, this is what I've picked up, saying like, I know these are values, but you want to change them to make it more reproducible or more like adaptive to a CI build.
Okay, great. So, any last words? All right. Well, I thought this was an interesting session, and I wish we had had more people to join us and participate, but that doesn't always happen. So I wish you a good evening and good luck. And for those of you who are going to do this again in Pittsburgh, you'll have a little more time there, and you'll have, more in-person contact. So that's great. So I think unless anybody has some last words, we'll declare victory here, and I'll wish you all the best of success.
Thanks, Tony.
Thanks,
Good.
Tony.
Thank you,
Thanks,
guys.
everyone.
Take
It was
care.
a pleasure to meet you
You're
all.
Likewise.
Yeah, nice to meet you.
Bye.
Bye.
Bye.